Year 12 and welcome to Purple Mountain Maths. Today we're doing the 2025 HSC paper for Maths Standard 2. This is part 8, covering question 38, 39 and 40, worth 11 marks. Question 38. A car's fuel efficiency is 30 miles per US gallon, and we're given this box which says 1 US gallon is 3.8 litres, corrected 2 sig figs, and 1 mile is 1.6 kilometres, corrected 2 sig figs. Question says calculate the car's fuel efficiency in litres per 100 kilometres, correct to 1 decimal place. Pause here to try yourself. All right, so we are given miles per US gallon and we want to work our way towards litres per 100 kilometres. So let's just do this step by step. So initially we know 30 miles per US gallon, and I know that a US gallon is worth 3.8 litres, so it's 30 miles per 3.8 litres, and now I want to get it into kilometres. 30 times 1.6 kilometres per 3.8 litres. So I'm actually working towards litres per 100 kilometres, so I'm just going to write those the other way around. 3.8 litres per, I might as well work out 30 times 1.6 now. 30 times 1.6. So that's 48 kilometres. So 3.8 litres per 48 kilometres, but I want to know the number of litres per 100 kilometres. And so this is unknown. So I can set up a cross multiply. 48x equals 100 times 3.8. So x equals 100 times 3.8 on 48. So I get 100 times 3.8 divided by 48. I get 7.916 repeated litres per 100 kilometres. Now they've actually asked it to 1 decimal place, so make sure you give them what they want. That's approximately 7.9 litres per 100 kilometres, and that's the answer. Question 39. After a dose of medication, the amount of medication remaining in a person can be modelled by the equation y equals ka to the x, where x is the number of hours after taking the dose and y is the amount remaining in milligrams. The graph shows the amount of medication remaining in a person after x hours. 2 points are also shown on the graph. Question says, using the information provided, find the amount of medicine that remains in a person when x equals 4. Pause here to try yourself. Okay, so I can see that they have given us those 2 important dots. So they've told us that 0,15 is on the curve, and so is 2,9. Take care to write those carefully. So y equals ka to the x. We know that at x equals 0, the answer is 15. So 15 equals a to the 0, but a to the 0 is just 1. So 15 equals k, so we know that k equals 15. That's a good first step. We also need it to go through 2,9. So we know at x equals 2, y equals 9. So 9 equals, now I just worked out that k is 15. 15a squared. So a squared equals 9 on 15, and a is the square root of 9 on 15. I'm getting closer, so I now know the structure of my equation is y equals 15. My a is root 9 on 15 to the power of x, and I'm interested in what's going on at x equals 4. So at x equals 4, y equals 15 root 9 on 15 to the power of 4, and that is 15 times 81 on 225. And my calculator says the answer equals 5.4. That's in millions. And that's my answer. Question 40. In a flock of 12,600 sheep, the ratio of males to females is 1:20. The weights of the male sheep are normally distributed with a mean of 76.2 kilos and a standard deviation of 6.8 kilograms. In the flock, 15 of the male sheep each weigh more than X kilograms. Find the value of X. Pause here to try yourself. All right, so I like to set this up with careful headings as if it was a simple ratio question. So my headings are going to be male is to female is to total. And I know that for every one male, there's 20 females, therefore 21 parts in total. But I know that there are 12,600 sheep. So I'm looking for these values. So the male value must be 1/21 of 12,600, and the female is representing 20/21 parts of that number, so that they add up here. So we can work out what that is. 1/21 times 12,600. I get 600 male sheep, and therefore I can do in my head that it's 12,000 females, so that they add up to 12,600. Okay, so I now know my numbers. I also know that that the males are normally distributed with a mean of 76.2. So a normal distribution means it looks like this. The mean is here, and we know that that's 76.2. We also know what the standard deviation is. We know that one standard deviation is 6.8 kilos. So let's work out how many we're interested in. 15 of the 600 sheep is what percentage? 15 over 600 given to me as a percentage is 2.5%. Now I know that one standard deviation is 68% of the values. I know that two standard deviations is 95% of the values. So with 5% split above and below, that means that 2.5% is above. So I'm interested, the top 2.5% of values have a z-score of 2 or more. So z equals 2. My z formula is score less mean over standard deviation. So I can evaluate that. If 2 equals the score less 76.2, which is my mean, over 6.8, then 2 times 6.8 plus 76.2 must be my x. I get x equals 89.8, and that's in kilos. B, The weights of the female sheep are normally distributed, but have a smaller mean and a smaller standard deviation than the weights of the male sheep. Explain whether it could be expected that 300 of the females from the flock each weigh more than X, where X is the value above. All right, so they're telling me that if this is the distribution for the males, the females is lower because it has a lower mean, but it also has a smaller standard deviation. So the females must look like that. The females have a mean which is lower, and a smaller standard deviation means it's even tighter. So let's work out where 300 of the 12,000 females is. 300 of 12,000 females is also 2.5%. The top 2.5% of scores have Z score of 2, but females' mean is lower. So the females, the location of the female's Z score is lower. The mean is lower and the standard deviation is lower. So the females have lower, tighter, i.e. less spread out, distribution. So the score corresponding to Z equals 2 for females cannot be at a score of X equals 89.8 kilos. So the answer is no. And that's the end of the paper. Thanks for listening to Purple Mountain Maths.